We said a couple of days ago that there were 4 properties of waves that were exhibited by electromagnetic radiation. Refraction was one of them. We said on that day that refraction is the bending of a wave when it goes from one medium to another. This is a picture, an actual photograph of refraction taking place here. You can see that the light is reflecting off of the pencil inside the water, and then as it leaves the water-air boundary, it changes direction and tricks our eyes into thinking that the pencil is bent. Now, why does that happen exactly? Refraction happens because the speed of the wave changes when it goes from one medium to the other. The speed of the light, in this case, changes when it goes from one medium to the other. I want to give you an analogy here right now to help you to understand how the change in speed results in that change in direction. Let's say that for whatever reason we have this parking lot, this paved parking lot beside this swamp. Now, there's, for whatever reason, soldiers marching in this parking lot. Maybe it's part of a parade or whatever. These soldiers are represented by these X's. They're all in a line like this. Now, if we look at these soldiers from above, it kind of looks like a wave front, right? It kind of looks like just a line, kind of like the crest of a wave. Now, let's fast forward, let's say 2 seconds into the future. These soldiers, because they're soldiers, do a good job of marching in stride. So when one soldier walks 2 meters in 2 seconds, then the next soldier will march the exact same distance in the exact same amount of time, right? So soldier number 1 is up here. Well, soldier number 2 is right here. Number 3 is right here. 4, 5, 6, and so on. But wait, number 7 has a little bit of trouble here right now, keeping up. How come?
He's hit a swamp.
He's hit a swamp, right? So soldier number 7 is right here. Soldier number 8 went into the swamp pretty much right away. Didn't get to march on the pavement at all. So soldier number 8 is right here. If we draw that line now that joins them, looking from above, then it's going to look something like this. Now, if we fast forward 2 more seconds down the road, then soldier number 1 is going to be up here, number 2, number 3, 4, 5. Look, now 6 is just barely into the swamp. 7 is well into the swamp. 8 is still well into the swamp. So 7 and 8 are definitely going slower. 6 has started going slower as well. Join those lines, or join those points together here, and we end up with something like this. Okay, 2 seconds into the future again. Okay, we start getting the same thing with even more of these soldiers. So now the wave looks like this if we look at it from above, or the marching of these soldiers, that is, looks like this marching from above, or looking at it from above. Now, let's draw an arrow indicating the direction that this wave front is traveling. In the pavement, it's traveling straight up, straight forward, right? Inside this swamp, it's changed direction like this. Why did it change direction? Well, because when it entered the new medium, at an angle that is, it changed speed. The change in speed resulted in a change in direction. Now, it also resulted in something else. Anybody catch what else it resulted in? A change in?
Velocity.
Well, the change in speed, yeah, change in velocity, change in speed, resulted in a change in direction, but also a change in? No? The wavelength, yeah. Look at the distance between the waves right here. This would be the wavelength. Look at the distance between the waves over here. This would be the wavelength. So as the wave goes into a new medium and slows down, the direction will change. The wavelength will also change. The wavelength will also slow down. Does that make sense? So as we go from one medium to the other at an angle, the speed will always change, which in turn causes the wavelength and direction to change. That's refraction. That's a property of waves, but it's a property that's exhibited by EMR, so of course, then EMR must be a wave. We're going to define refraction as the bending of a wave. The bending of a wave when it passes from one medium to another. And this happens, as we just saw in our analogy, it happens because the wave is changing speed. Either speeds up, or in the case of the analogy that I just showed you, it slows down. Now let's define another term that describes how much refraction will take place, how much the wave will bend as a result of that change in speed. That term is called the index of refraction, or sometimes you might hear it called the refractive index. There's a few of you that wear glasses right now. When you go get glasses, you can pay a certain amount of money for your glasses, or they'll say, oh, hey, if you want higher index lenses, then you pay a little bit extra money, right? You ever heard them say that? Okay. High index lenses. Okay, that means that they would have a higher index of refraction, which means that the wave, or in this case light, would bend more, which is beneficial to you if you're wearing eyeglasses, because if the light bends more due to the higher index of refraction, then it means that your lenses can be thinner and still accomplish the same thing. The benefit of high index lenses is to give you thinner lenses. Sorry? Why do you want thinner lenses? Well, the vast majority of people, especially young people, will have what we call concave lenses. They're converging lenses, concave lenses. Sorry, diverging lenses. Concave, but diverging. It means they're thinner in the middle than they are at the edges here. And that allows light, as it goes through, to spread apart. Then it goes through the converging lens that's in your eye. It's actually built into your eye and causes it to refract and converge at the retina of your eye. If you don't have those glasses that are thinner in the middle than they are at the edges, then the rays of light will refract in the wrong place and not converge and focus on the retina of your eye. So they need to be thicker at the edges. We'll talk more about this when we get into lenses later on next week, but they need to be thicker at the edges than they do in the middle in order to cause the right amount of refraction of the light to cause the image to be formed on the retina of your eye. Now, because they're thicker at the edges than they are in the middle, if you have, the lower the index of refraction you have, the more pronounced that has to be. The more glass or plastic that has to be used in order to refract the ray. So that means that if you don't like the thickness of the lenses at the edges right now, wait till you use a lower index of refraction and it becomes even thicker. Okay? My wife has, my eyes are about -3, I think -375. Anybody know what your prescription is? Yeah? Okay, that's almost exactly mine. I have what's called an astigmatism, and some of you guys might have an astigmatism as well, where basically I have to have the prescription on 2 axes. So it's not quite as simple as one axis of prescription. It's 2 axes of prescription, 2 different axes of prescription, I mean. So it's not uniform. It's not a big deal, but it's not exactly -375 because of that. It's -375, and then there's another number that's associated with it. My wife has a prescription of about minus, I think it's -9 something. Like, if she takes her glasses off, she's effectively blind. If she takes her glasses off, she can't see a thing. So we spend a fortune on her glasses so that they're not so thick, right? And they're not bad. Like, when you spend the money and get a super high index lens, they're not bad. They don't look different at all. But if you just go with the normal refractive index in the lenses, then they're going to be like super thick at the edges. And you don't want that, right? So the index of refraction is the ratio of this, we define it as the ratio of the speed of light in a vacuum, which is always 3 times 10 to the 8 meters per second, to the speed of light in the medium. Now, what does it really do? What does it really tell us? It tells us how much light bends. So my wife's glasses that have this super high index of refraction bend light more. So the index of refraction measures how much light bends when it goes from one medium to the other. The higher the index of refraction, the more light bends. Why? Well, because the higher the index of refraction, the more the change in speed. Right? Light slows down more when it hits my wife's lenses than it does when it hits my lenses. that means the index of refraction is higher, and it means that the light will bend quicker or more as a result of that, meaning that she needs, well, if our prescription was the same, her lenses could be thinner than mine. Now, her lenses aren't thinner than mine because her prescription is so high, but her lenses aren't thicker than mine because her lenses bend the light quicker. They have a higher index of refraction. The technical definition, though, is the ratio of the speed of light in a vacuum to the speed of light in the medium. The symbol for the index of refraction is n, lowercase n. There are no units associated with it. It's just a number, n. It is equal to c. C is the speed of light in a vacuum. Which is 3.00 times 10 to the 8 meters per second. So that number will always be the same. It's a constant, 3.00 times 10 to the 8 meters per second. V is the speed of light in the medium. And that speed of light in the medium will be either equal to 3 times 10 to the 8 meters per second or lower than 3 times 10 to the 8 meters per second. It will never be higher. That means that the index of refraction will be found by dividing two numbers, the top number always equal to or greater than the bottom number. That means that the index of refraction will always be 1 or bigger than 1. The smallest index of refraction that we can have is 1.00. And the index of refraction for a vacuum or for air is 1.00. That tells us that when light goes from a vacuum to a vacuum, it doesn't bend. As we go from, say, vacuum to glass, where the index of refraction is about 1.5, it bends. When it goes from vacuum to, let's say, diamond, which has an index of refraction of 2.4, it bends more because it changes speed more, because this value of V on the bottom is smaller than it is for air or vacuum or glass. Now, I'm going to throw something else at you now. The index of refraction for, well, we say for glass, there's different kinds of glass, but let's just say glass, okay, one general category of glass. Let's say it's 1.5. Well, it's 1.5 for one color of light, but it's a different value for another color. The reality is that every material has a slightly different index of refraction for each different color. And that results in a process called, or a phenomenon called, dispersion. When you shine light, white light, which is all the colors of the rainbow, right? You take a flashlight, which is considered to be white light, all the colors of the rainbow, and you shine it through a prism, a piece of glass or a piece of plastic or acrylic or something like that, it will split up the light. It will cause it to break apart into its component colors, which are, of course, red, orange, yellow, green, blue, indigo, and violet, Roy G. Biv. Why does it do that? Well, because this glass has a slightly, this should say slightly, different index of refraction for each frequency. The index of refraction of this glass for red light is less than the index of refraction of glass for violet light. That causes red light to bend less than violet light. And because red light bends less than violet light, it ends up coming out on the other side in a different place. Low frequencies produce a lower index of refraction and therefore bend less or disperse less. High frequencies produce a higher index of refraction and therefore bend more and therefore disperse more. And you end up with this spectrum, this continuous spectrum, we call it. Continuous because it's one color transitioning into the next on a screen on the other side. This is dispersion, right? This is dispersion taking place. The atmosphere acts essentially as a prism. It's the moisture in the atmosphere, right? It's all kinds of things in the atmosphere, but particularly the moisture in the atmosphere. That's why you tend to see rainbows after rain as opposed to any other time. Right? All kinds of things in the atmosphere can cause dispersion, but particularly the moisture, the water droplets can cause the dispersion. And what do you see there? Well, you see a spectrum, a continuous spectrum. Red, orange, yellow, green, blue, indigo, and violet. Which one is on the top? Red. Because red light bends the least. Red light refracts the least. Make sense? Let me show you another one. This one I got to draw, though. This is not going to be to scale, by the way. Here's the Earth. You're going to see in a second that it's not to scale, because this is the sun over here. Here's the atmosphere surrounding the Earth. Now let's say that atmosphere is it's got some water droplets in it, like it always does. Even if the air is dry and it's a clear sky, there's always moisture in the atmosphere. But maybe it's got some dust in there as well. Maybe it's like the temperature has changed the index of refraction. So temperature can change index of refraction, right? There's air in there. There's nitrogen in there. And the most common element in the atmosphere is nitrogen, right? So clearly there is an index of refraction. And that index of refraction can change depending upon conditions in the atmosphere. But right now, it's a certain value. Okay? Now, white light, or yellow light, because that's like what we perceive sunlight to be is yellow light, but we call it white light, coming from the sun, goes like this. I mean, it comes off in all different directions, right? But I want to look at particularly at this ray of sunlight. When it hits that atmosphere, it bends. But because this atmosphere has a slightly different index of refraction for each color of this white light, then we get a phenomenon called dispersion. Which color of light bends the least? Red. So we get this. Okay, which color of light bends the most? Violet. Yeah, violet. Blue, indigo, and violet. So we get this, right? So far, so good? Okay, you got a person standing right here at this point. What time of day is it for that person? What time of day is it? It's sunrise or sunset. How do you know? Well, look at where the sun is relative to that person. Like the sun is just coming up. The person can barely see the sun, right? The sun is just coming up or just going down. What color is the sky sometimes at sunrise and sunset? Reddish. Right? And why is it reddish? Because red light refracts the least, because the index of refraction for red is the least. Okay, what time of day is it for this guy right here? It's like noontime, right? It's the middle of the day. Look at where the sun is. It's right above him or her. What color is the sky? It's blue, right? Because blue light refracts blue, indigo, violet light refracts the most. Now, why don't we see it kind of like, why don't we see it purple? Why don't we see it purple? Well, it's not quite as simple as this, right? Because there's other rays of sun coming in, right? Like this ray comes in right at it, right? And because that's going straight at it, that white light doesn't split up. If you have white light going straight into something at 90 degrees, it doesn't split up. So really what you get is a combination of colors, but you can see why in the middle of the day it would be more blue than it would be red. And at sunrise, sometimes, depending upon the index of refraction, we would get more red than we would blue. Does that make sense? Dispersion. Okay? Red light refracts the least. Blue light, indigo, violet refracts the most. Red light produces the smallest index of refraction. Violet light produces the biggest index of refraction. Okay, that's dispersion. Now, we're going to end it today with a little bit of math. We call the equation that describes all of this Snell's law. By the way, this table that's on the right-hand side, don't copy that down. Okay, don't copy that down. Those numbers will be given to you if you need them for a particular question. They'll be given to you. These are just various indices of refraction for different materials. Now, you understand that, like I gave you the index of refraction for ethanol, it's 1.37. It actually varies a little bit, right? Depending upon the color, right? What color of light is being used. But on average, it's 1.37 for ethanol. On average, it's 1.54 for ruby. On average, it's 2.42 for diamond. The equation that we use to describe the bending of the light when it goes from one medium to another is called Snell's law. And it's got 4 parts to it, but the good news is you only ever need to use 2 parts. Part number 1 is the ratio of the sine of the angles. So if we have a ray of light going from medium 1 to medium 2, we'll call this theta 1 and this theta 2. The angle of incidence, the angle of refraction. Theta 1 and theta 2. The ratio of the sines of those angles is equal to the ratio of the speeds in those 2 media. So however fast the light is moving in medium 1 compared to the speed of the light in medium 2, which is equal to the ratio of the wavelengths. Which, be careful on this one. Okay, sometimes you get caught up in saying, oh, theta 1 over theta 2, V1 over V2, lambda 1 over lambda 2, N2 over N1, N2 over N1. Watch that. It's on your data sheet, so you can copy it straight out, but sometimes we just get like in the habit of writing 1 over 2, 1 over 2, 1 over 2, not 2 over 1. Yep.
Can I ask why that's the case?
Yes, you can ask why that's the case. You can ask anything you want. Now, I'm not going to answer it, but you can. No, I will answer it. That's a good question. It's a good question. Why is it the case? Why is it 1 over 2, 1 over 2, 1 over 2, and then 2 over 1? Well, the equation that we have for index refraction that we just gave you a few minutes ago, which, by the way, is not on your data sheet because it's more of a definition of index of refraction, C over V. Okay? So that means that it's 3 times 10 to the 8 divided by the speed of light. Okay? The higher the value of the speed of light, okay, the lower the index of refraction. The higher the value of the speed of light, the lower the index of refraction. So like if we've got, let's say we've got glass, where the index of refraction is 1.5. For glass, the speed of light would be 2 times 10 to the 8 meters per second. Agree? So 3 times 10 to the 8 divided by 2 times 10 to the 8 gives me a value of 1.5. Now, let's go zircon. Let's say the index of refraction is 2 there, just for ease of math. Okay? For zircon, the index of refraction is 2, and the speed is 1.5 times 10 to the 8. So as n goes up, V goes, as n goes from 1.5 to 2, V goes from 2 to 1.5. As n goes up, V goes down. That's why it's V1 over V2, lambda 1 over lambda 2, N2 over N1, because the index of refraction is inversely related to the speed of light in that medium. Does that make sense? Good question. What is this equation used for? To describe the bending of the light when it goes from one medium to another. So let's go back to that very first picture that I showed you. This one. It's to describe, among many other applications, what this pencil is going to look like in the water, how much the pencil bends in the water. And I'll show you several applications of this as well as we go through the next couple of days here. Yep.
It describes the way in which...
It just describes mathematically the bending of the light. So we've described, like through here, we've described qualitatively what's happening. Like what's happening? Light bends, right? And bends because of this, and this is the colors that bend more, and whatever. This is what describes mathematically what's happening. Kyle, you had a question? Absolutely you will. Yeah, you will. But you're never going to use all four parts of it at once. You'll use part 1 and part 2, or maybe use part 1 and part 4, or maybe use 2 and 4, or 3 and 4, or 2 and 3. You're always going to use 2 parts. And of course, that just depends upon like what you're given and what you're asked for, right? Okay, it tends not to be crazy hard. The trickiest part of it, honestly, is because it's a fraction and because we have a trigonometric function in there, sometimes it becomes a little bit of a challenge for some people in rearranging. But it's not usually very hard determining what part of the equation to use. Okay, I want to do 2 examples, and hopefully we have time to do both of these before we take off here. First example, what's the speed of light in a ruby? Well, I'll tell you what, the easiest way to do this is just to say n is equal to c over v. V is equal to c over n. C is 3 times 10 to the 8 meters per second. The index of refraction for ruby is given to us back here. It's 1.54. We do the math there, and the speed of light in a ruby works out to be 1.95 times 10 to the 8. We know we're going to get a value smaller than 3 times 10 to the 8, right? Because 3 times 10 to the 8 is as fast as light can travel. Example number 2, and this is the last one we'll do here. It says light passes from water to ice at an angle of 40 degrees. What's the angle at which the light struck the water-ice boundary? Let's draw a picture of this. Okay, here's the liquid water. Here's the ice. The index of refraction of the water, of the liquid water, is 1.33. And of the ice, it's 1.00. Let's call this medium 1 and medium 2. So we're going to say N1 is 1.33, N2 is not 1.00, 1.31 it should be. And those are on our data sheet, not on our data sheet, but those are on the table that I gave you back here, right? And it's on the worksheet that you're going to be working on. It's on there as well. So you don't have to memorize those numbers, whatever. You see, ice is 1.31, water is 1.33. So liquid water, 1.33, ice, 1.31. Let's say we've got this ray of light that's coming in like this. The angle of incidence is what we're trying to find, theta 1, measured from the normal line. Okay, a normal line, normal in physics means 90 degrees. Remember normal force in physics 20? Normal line, 90 degrees to the boundary. We always measure it from the normal line. Now, theta 2, also measured from the normal line here, we know the value of this. It says light passes from water to ice at an angle of 40 degrees. It passes into the ice at 40 degrees. We want to know the angle at which the light struck the water-ice boundary. So we're going to say sine theta 1 over sine theta 2 equals N2 over N1, 2 of the 4 parts of the equation, right? Sine theta 1 over sine 40 equals N2, which is 1.31, over 1.33. So let's rearrange this now. Let's say sine theta 1. You can solve part of this before you start rearranging it or whatever. Solve for theta 1. It's the inverse sine of all that over here on the right-hand side. And when we get that, we end up getting 39.3 degrees. So, like, just 2 seconds before you take off here, guys. I know the bell's gone. Works out to be 39.3 degrees. Okay, this kind of comes back a little bit to what we were saying over here a few minutes ago, right? Or the question we had over here a few minutes ago. Why is it N2 over N1, whatever. Look at what's happening here. The index of refraction goes down. The speed, because it's inversely related, will go up. The wavelength will go up. And the angle will go from 39.3 to 40 is up. So when N goes down like it did here, V goes up lambda goes up, and theta goes up. That's how I knew when I was drawing this out to draw theta 2 bigger than theta 1. I knew it was going to be bigger because n was smaller. Make sense? Okay.